All right, let's jump right into this explainer with a massive, mind-bending question that is currently keeping hardware engineers awake at night. What happens when our data storage physically cannot get any smaller? We spent decades shrinking technology to fit entirely new worlds into our pockets, but physics has a hard limit, and we are crashing right into it.
Welcome. Today we're unpacking a really fierce, high-stakes battle going on right now between the aging flash memory, the tech currently inside the phone or computer you're using, and this microscopic, completely game-changing challenger called RRAM. The winner of this showdown is going to dictate the future of computing, artificial intelligence, and basically how we build devices for decades to come.
To make sure we've got a solid grip on this, here's our roadmap. We're going to look at the flash memory wall, how RRAM actually works, put them head-to-head, explore how this powers edge AI, and finally, look at the roadblocks in the way of a true memory revolution.
Okay, Section 1, the flash memory wall and hitting physical limits. We really have to start by understanding the problem.
So traditional NAND flash memory, which absolutely dominates the market today, works by trapping electrons to store your photos, your apps, your entire operating system. But here's the kicker. As we push flash to sub-10 nanometer levels to pack more and more data into a smaller space, those tiny memory cells get way too crowded. The trapped electrons literally start leaking out and interfering with the cells next door. It's called cell-to-cell interference, and it causes data corruption. Basically, the smaller we make standard flash, the less reliable it becomes.
Moving on to Section 2, how RRAM works, the microscopic challenger. To get around that scaling limit, engineers needed a totally fresh approach. And that brings us to resistive random access memory, or RRAM. Instead of trapping electrons like flash does, it relies on a completely different physical mechanism. Let's actually look at how this works at the atomic level. It's a neat three-step process. RRAM uses an insulating layer, typically something like hafnium oxide, sandwiched right between two electrodes. When you apply a very specific voltage, oxygen ions in that oxide layer literally shift their position. And that movement, it creates a tiny conductive filament. It's basically a microscopic bridge that lets current flow through.
So the big takeaway here is that RRAM is literally a physical nanoswitch. You apply voltage, a filament bridge forms, resistance drops, and boom, you've stored a 1. Reverse the voltage, the bridge breaks, resistance goes up, and it stores a 0. It's just snapping open and closed in a literal flash, completely bypassing those electron leaking issues we see with traditional memory.
All right, Section 3, RRAM versus flash memory, the showdown. Let's put these two head-to-head to see exactly why the tech world is so incredibly hyped about this.
When you compare them structurally, flash memory requires this clunky block-level erasure, meaning if you want to change a single piece of data, flash forces you to erase and rewrite an entire block of data. It's incredibly inefficient. RRAM, though, it simply changes resistance states at the individual byte level. It is nimble, insanely fast, and avoids all that heavy background processing that older flash tech needs.
And wow, check out the sheer efficiency. Because RRAM doesn't have to pump high voltages just to trap electrons, it consumes roughly 1/10 the power of standard flash memory. 1/10. For anything running on a battery, that metric alone is an absolute game changer. Looking at the raw numbers side by side, honestly, it almost seems like an unfair fight. Flash writes in milliseconds, RRAM writes in nanoseconds. Flash needs a massive 15 to 20 volts to program, RRAM needs just 1 to 3 volts. And look at the cycle endurance. Typical flash wears out after a few thousand erase cycles. RRAM boasts an endurance of up to 1 billion cycles. It's faster, it's vastly more durable, and it barely sips any power.
Section 4, powering edge AI, or computing where data actually lives. This massive leap in speed and efficiency isn't just a nice-to-have feature. It's exactly what we need for the exploding field of edge AI. We're talking about running complex artificial intelligence directly on devices like smartwatches, car sensors, and remote cameras without having to send all that data back and forth to the cloud.
But here's the huge bottleneck the AI world is fighting right now. Our logic processors, the actual brains doing all the heavy math, are scaling down beautifully to super-fast 3-nanometer processors. But embedded flash memory, it's practically stuck. It really can't scale effectively below 28 nanometers, so you physically cannot put them on the same tiny chip anymore. Manufacturers are forced to use clunky, expensive 2-chip setups, shuffling data back and forth. It drains your battery and totally kills performance.
RAM completely fixes this because it can scale down alongside those 3-nanometer processors. Like this great quote from Chemical Reviews points out, it unlocks in-memory computing,
By placing RAM directly next to the compute logic on a single die, we can compute directly within the memory itself. You slash the power-hungry data movement, meaning AI systems can wake up instantly for things like real-time facial recognition or autonomous driving without a single millisecond of lag.
Which brings us to Section 5, Roadblocks to the Future. The complications. You're probably thinking, well, if RRAM is so vastly superior, why isn't it already in my smartphone? Well, as with all bleeding-edge tech, there are some pretty tough hurdles. Physics is tricky. Creating those microscopic conductive filaments is a highly volatile process. The bridges can get unstable over millions of cycles. On top of that, these memory arrays are super susceptible to radiation soft errors from highly energetic cosmic rays hitting the device. Plus, in these really dense crossbar arrays, you get what are called sneak path currents, basically unintended electricity leaking into the wrong cells and causing misreads.
And we're not just talking about minor glitches here. Research out of the University of Waterloo showed that without automated detection and correction, these radiation soft errors and filament instabilities could degrade the accuracy of an RRAM-based AI system by over 48%. I mean, think about it. If your autonomous car's AI is suddenly 48% less accurate, yeah, that is a critical failure.
Plus, there's the whole business side of manufacturing. Flash memory has been perfected over decades, right? It boasts yield rates of over 90%, making it incredibly cheap per gigabyte. RRAM production requires wildly expensive, precise nanoscale engineering, and its manufacturing yield right now is hovering around 60 to 75%. Simply put, it's just harder and more expensive to make a reliable RRAM chip today.
Finally, Section 6, the horizon. Who is going to win this memory race? Despite those roadblocks, the entire industry knows that the flash memory wall is rapidly approaching. Major players are not backing down. They are rushing to commercialize this.
Mapping out the industry, everyone is placing massive bets. You've got Intel looking into hybrid phase change stuff like their Optane technology. Samsung is hedging its bets, heavily researching ultra-fast RM arrays while also pushing standard VNAND to its absolute physical breaking point. Meanwhile, you've got agile challengers like Weebit, totally focused on pushing embedded ReRAM specifically for low-power edge AI devices.
Ultimately, perfecting this tech could fundamentally rewrite how every single computer, phone, and smart device is built. Just imagine a device where your short-term working memory, your RAM, and your long-term storage are totally merged into one unified lightning-fast layer. No boot times, zero loading screens, just instant, incredible performance.
So, as we wrap up this explainer, you really have to ask yourself, how much longer can traditional flash hold out before the microscopic nano switches take over? Will your next device compute entirely within its own memory, or will the flash empire hold the line just a little bit longer? Thanks for exploring the future of memory with me, and I'll catch you next time.